So I'll hand over to Osbert now, who will tell you about that.
Okay, so thanks for the introduction, and also thanks for coming to this talk. I'm going to talk to you some of the interesting things performed in our laboratories for the study of the liquid crystal surface anchoring structures using these dual polarization interferometries. Okay, so let's start from the purpose of this research, which is said to be for the understanding of the nematic liquid crystal surface alignment on the solid substrate. And the main reason of this research is for there is a lot of research interest expressed in the surface diffuse alignment, because this is quite essential for the nematic liquid crystal device operations. And also there are a lot of fundamental interest also for this understanding of these molecular absorption mechanisms on the solid surface. So for the outline of this talk, I'm going to first of all give you a general introduction for the nematic liquid crystal anchoring phenomena, and followed by a fundamental introduction for the DPI technique. And then I'll talk about the DPI study for the 5CB anchoring structures by giving you a theoretical foundation as well as the experimental analysis, respectively. And what we see here is it's basically a chemical structure of the 5CB molecules by having this biphenyl polar group combined with a hydrocarbon polar group. So for the general nematic liquid crystal anchoring structures, we at least have three main types. And the first type, which is also the most important one, is for the NCB molecules anchoring on the barycentre-like surfaces with this sort of tri-layer structures. And just bear in mind, the NCB molecules say the most important molecules in the liquid crystal systems. So in these tri-layer configurations, we'll have the TLT compact monolayers, which is covered by an interdigitated bilayer with the reduced polar angles. And this configuration is by convention called the metastable precursor films. And we could also have this sort of tilted monostable anchorings for the NCB molecules anchoring on this topographic point surface. And with all of the molecules actually taking a single azimuth orientations, which is prescribed by these microgroup directions on the point surface. And also in another case, we could have a homeotropic anchoring on this aliphatic change. And one of the examples is the NCB molecules anchoring on these non-voltage films. We see a vertical alignment of molecules, and this is because of the interactions between molecules and the hydrocarbon channels. So, there are some of the issues that is associated with the anchoring structures, which actually increases the complexity of the studies. So they are, first of all, the anchoring structure is strongly dependent on the substrate morphologies and also substrate chemistries. And then the layer orientation is also strongly correlated with the film thickness and also the molecular densities because of the self-organization behaviors of the liquid crystals. And also, we can easily get this molecular aggregation and also the molecular condensate on the surface and lose the molecular alignment. So I'm going to talk about the foundation of this dual polarization interferometry techniques. So basically, we have 5-layer dual slab waveguide structures, as shown in this picture here. We have an R70 waveguide in here, which is used for the molecular depolation on the surface. And we also have a lower waveguide or lower reference waveguide in here. So what we have is the laser beam in both polarizations impinged on this end face of the waveguide to excite the two fundamental modes that can be propagated along the structure in both T and TM. And just remember, the T is the transverse electric field mode with the electric field direction along the span. And the TM mode is the the transverse magnetic mode with the magnetic field directly in its plane, so the electric field will be out of the plane. So the two modes from the end phase of this waveguide will be diffracting into the free space to and also interfere with each other to construct a sort of cross-Young fringe. Of course, the Young's fringe will contain the phase informations. And basically what we see here is fringe pattern intensity, which is captured by the camera in this detected fringe. And so I'll show you the movie, which is basically you the fringe pattern shift, a general shift, and due to the molecular deformations on the waveguide surfaces. So for the main optical profile of the mode that is propagated on the structures, we have most of the optical energy is confined in the central region of the waveguide, and by having an evanescent field penetrating into the free space, like this, in terms of the exponential decays. And so this is the basic electric field profile of the mode, and that can be decomposed into two parts. The one part is for the propagation wave functions, written in this form. And we can define the propagation constances of the mode, beta here, to represent some of the phase informations of the mode for the propagations. And also the other part is for the transverse field distributions along the X directions. So the interesting thing is that if you deposit any molecules in this interface, you're actually going to change the refractive index of the interface, which will then cause the perturbation to this decay constant alpha here, and also cause the perturbation to the propagation constant vector here. So the changes of the propagation constant will then give changes to the phase informations, which will eventually be revealed by the fringe pattern shift. So when you deposit molecules on this interface by forming a sort of ultra thin layers with thickness which is smaller than this field intensity decay dates, roughly about 8 nanometers, you're actually going to giving a significant perturbation to this propagation constant. I'm going to introduce a new term here, which is called the effective index, M here. So the propagation constant can be written in the multiplication of the effective index as wave vectors. And just bear in mind the effective index of the waveguide is very characteristic parameters, which can contain all the optogeometric information for all the waveguide layers. And of course, it's going to include information from molecular assays. Okay, so when you put the molecules on this interface, you're going to change the effective index in both modes, and also gives optical passband changes, as well as a phase shift. Just remember these two terms here is the effective index in both T and TN mode, and also the phase change here is for the phase change for the T and TN mode. So if you measure phase change, you can get a very easy calculation for the effective index changes. So to resolve the active optogeometric structures, we're going to assume there's a pure dielectric stack for the waveguide materials, and we can compute the starting eigenvalues for the starting propagation constant and the starting effective index. And by taking the experimental data for the phase change, which can be easily converted to the respective index changes, we can then compute new eigenvalues and also new effective index, which will allow us to compute the active refractive index and the active thicknesses. And if you do it in both modes, in both T and TM mode, it's going to be equivalent to solving the simultaneous equations to find this unique pair of the index and the thickness of the layer. So basically what we show here is a fringe pattern shift for certain phase change taken from the real experimental data when the molecules are quantitated. So quantitatively in the experiment, but we'll have a significant enhancement of the effective index in two modes when the molecule is deposited. So by having a certain pair value of the effective index, and also by assuming there is optical isotropy of the actin, and also a uniform coverage of the layer surface, we can get correlation patterns between the refractive index and also the thickness of the actin. And actually what we show here is two correlation patterns for both T and TM modes for certain values of the effective index in two modes. So the intersection of these two patterns will give you a unique pair of the refractive index and thickness of the actin. So just bearing in mind all of the introductions I gave for the basics of the DPIs, I'm just going to talk about the DPI study for the 5-3D anchoring structures. And this is our experimental setup. And so I'm going to inject the 5-3D molecules in these thermal evaporators. And we'll heat it up to 90 degrees. And we're pushing the air to generate some sort of liquid crystal flows into this chamber here, which is built upon the waveguide surface. So part of the molecules will be absorbed on the waveguide surface to cause the DPI phase changes. And just remember that the waveguide materials is made by the silicon oxylides. So we are basically talking about the 5-3D anchoring structures on the silicon oxylide surface. So because we're talking about the liquid crystal system, which is essentially anisotropic, and so we can't just follow the calculation method which is described above for the isotropic system. So what we do here is basically we have birefringent LC actin on the surface, and we assume there is an adenosine degenerate anchoring of the molecule on the silicon oxylides surface. And this is just because the silicon oxylides surface is essentially isotropic. So the molecule could have all possible orientations in the adenosine plane. And by just taking a single polar angle, which is determined by the anisotropic interactions, just remember the only is molecular orientations. So for the molecular dielectric tensors, can be easily written in this form, we have N naught and NE to be the ordinary and disorderly refractive index. And for the experimental dielectric tensor, we use the coordinate transformation to transform the dielectric tensor from the molecular frame to the experimental frame. And this is our computational result. For the refractive index in both Z and Y directions as a function of the polar angle. And of course, the index in Z and X directions will be equal to each other because of the surface isotropies. So I'm going to introduce a new assumption here, which is called the linearity assumptions. We'll have, provided the actin thickness is quite small, we can assume the effective index of the waveguide will be linearly correlated to the actin thickness. We can write the effective index of the both modes to be in a simple form. And this actually relationship could be perfectly proved by theory. Now, of course, the A and B is the linear perturbation constants of the two modes, which is only a function of polar angle and the actin thickness. So the phase changes could be easily transformed in these relations using A and B, the perturbation constants, and phase change ratios will be the ratio of the perturbation constants of the two modes, which can be easily computed. Right, okay, so this is our computational result for the ratio of the two perturbation constants as a function of the polar angle with this sort of interesting shapes. And we actually assume there is a uniform layer coverage on the surface. And this graph will constitute the theoretical foundations of our experimental analysis. So let's look at the experimental result for the 5 molecules absorption of the silicon nitride. What we have here in the experiments, linear changes of the phases as a function of the depletion time, which is quite normal because the molecule is static on the surface. But if you plot the phase change ratios, some of the interesting things happens. And just bear in mind that I use the T phase changes as x coordinates to represent the depletion quantities. So according to the curvature changes of this diagram, we can basically classify it into 3 different phases of the depletions. For the first phase is in the region A. What we see here is a big fluctuation of the ratios, which means we have dilute molecules absorbed on the surface. There's no layer formation at all because the molecular rotation is not detectable at this time. So, but from the start of the region B here, when the ratio is initially stabilized, and also from the ratio values combined with computational result, we can easily get the angle to be polar angle to be 85 degrees, which means the molecule is like completely flat on the surface. But to the region B, to the end of this region B, according to the ratio values, we can then get the polar angle to be 56 degrees, which means the molecule is standing up somehow by tilting away from the surface. So what happens to this region B is essentially a monomer condensation in the evaporation of the molecule on the surface by having molecules standing up and tilting away from the surface. So, and the reason of this phenomenon, I think probably because of the self-organization behaviors of the liquid crystals. So, in the region C here, we see a flattening out of the curve, which probably means there is a starting of the second layer depletion due to the depletion curvatures. So for the exercise of the identification of the monomer thickness, I'm going to present the 2 methods here. The first method is we use the average isotopic refractive index from the liquid crystal bark combined with the measured effective index changes. And we can compute the effective isotopic thickness of the atmosphere. So this 2 thickness here is the 2 characteristic thickness corresponding to T and TMO, calculated by using the 2 phase changes and also this average isotopic refractive index from the bulk. So by taking this the weighted average of the 2 thicknesses, we can get the effective isotopic thickness of the atom. And also the second method is just a simple geometric thickness estimation from molecular dimensions. And we use thickness calculation by the simple cos and sine relations if you load the molecular weights and density once. So the setup here is just the polar angle, which is taken from the experimental ratios. This is the calculation result for the thickness of the monomer. So from the starting of the region B, when the molecule is lying completely flat, and after the calculation of these 2 thicknesses here, what we found is the isotopic thickness is smaller than the geometric thickness. And in the ideal case, it is impossible. So the reason that can explain this is that the assumed bulk liquid crystal refractive index used in this isotopic thickness calculations is actually overestimated in the real monomer system. So the real monomer refractive index will be smaller than the refractive index in the bulk, and also with a density smaller than the liquid crystal bulk. So what we can say is the monomer is dilute at this stage. But however, to the end of this region B, when the molecule is standing up somehow, and also after the calculation of the 2 thicknesses, we found the isotopic thickness larger than the geometric one. So following similar principles, we can say they assume bark as a liquid crystal refractive index in this isotopic thickness calculation is actually underestimated in the real modeling system. So the real modeling refractive index and the density also will be larger than the index and density in the liquid crystal bark. So there might be a qualitative conclusion that the monomer in this stage is overgoes, it is approaching to the solid phase because the density is even larger than the liquid crystal bark phase. So, and the reason might be there is interdigitation to second layer to this first monomer. So in this region C here, we see a subsequent deposition will lead to the Martinet constructions, and also the orientation of the orientation detection of this Martinet will be very challenging. So for the final sections, what we did here is 5 dB absorption on the LB functionalized surface. And all we did is we evaporate the 5 dB molecules of this B-type cadmium alkylated LB film. And what we found from the experimental data is the fringe contrast decrease here. So the only reason that can explain this is we are getting a molecular aggregate formation on the surface, which actually causes a lot of optical scatterings. And the optical scattering of the surface actually will increase the optical loss of energies in the upper waveguide, which will then lead to the fringe contrast decreasing here. So of course we are getting a non-uniform coverage of the layer. And I would say the theory here then will not be favorable to use for the data analysis, because when we talk about the theory in the polarization constant calculation, and the ratio calculation, we actually assume there is a uniform coverage. So this is not applicable here. But still, from the experimental phase check ratio patterns in here, we still see a very significant enhancement of the ratios, which might mean there's a qualitative polar angle increases from a smaller angle at this stage, where the ratio is in about 0.9 here, to a larger angle where the ratio is in about 0.94 here. So we could also say there might be anchoring structure transitions from the more homeotropic one, which is vertical one, to a more planar one. So I think for summary, we have constructed a model to map the phase changes ratios to the liquid crystal anchoring polar angles. And we also deposited 5 steady molecules on the silicon isolate surfaces, and we found from dilute to the condensed phase of the compact molar layer. And the molecules actually gradually tilting away from the surface. And the polar angle and the thickness characterizations matches quite well with the previous observations. And we also deposited 5 steady molecules on this LV functionalized surface, and qualitatively observed these anchoring structure transitions from a more homeotropic one to a planar one. So the future job might be the determination of the Martinet orientations of the liquid crystal anchoring films, provided the film will have very good weighted behavior, which means we're not getting the aggregate on the surface. So I think I will finish here by acknowledging the effort from my supervisor, Graham Cross, and also Merrick, who actually did a lot of LV experimental work, and Chris Pearson from the engineering department, who actually did the LV substrate preparations, and also Dan Coast, who gives the essential helps in chip preparations. And I also want to thank 2 of my funding agencies, the Barfield Group and the EPSRC, and also thanks for your attention.
Okay, yeah. Any questions for Osbert? He's cool as you.
Yes. Could you show, I think it's slide 11 again, there was the geometry of all this. And say a few words on sort of the dimensions and... 11, yes. sort of what there is your your fluid cell, whatever you call it, and so
It's
there.
okay.
Hmm?
It's okay.
Yeah, and then there is a certain length scale over which you get sort of this interaction with the layer structure.
Right.
The lateral length scale, what that is?
Well, that is just chocolate, the crystals, and we heat it up to very high temperatures
No,
and evaporate.
It's the window length, the chip window length.
Right.
Just wants to know the chip window length, the general scale of the diagram,
Okay.
the interaction length on the chip surface.
Oh.
What is that then?
I think I'm not quite following. So the molecule is just deposited into this window in this waveguide surfaces and absorbed on the surface.
It's about, but the window length is about 12 millimeters long.
Yeah, yeah.
So it's really
Yeah.
Macroscopic.
That's right. It's quite a large interaction area.
Okay.
Yeah.
That's right. And with your nice technique, you could cut that down if you needed to, because your signal seems to be good.
There's plenty of sensitivity. Yes.
Yeah.
I mean, we're getting lots of sensitivity. So it could be reduced. The window length could be. These chips are